Somewhere beneath the quiet fields between France and Switzerland, inside the coldest place human beings have ever built, colder than the empty space between the stars, a machine spent years slamming pieces of matter together just to glimpse the first instant of creation. And in the wreckage, again and again, it kept finding something that was not supposed to be there. Not a new planet, not a new star. A faint, stubborn wrongness in the empty space itself, an unseen thumb pressing on the scales of reality, as if the universe were quietly breaking its own rules. The scientists checked their instruments 1,000 times over, praying for a mistake. The mistake never came. And then, its questions only deeper than before, the great machine slowly went quiet, its beams shut down, and the world moved on without quite noticing what it had seen. So what exactly did it find in all that emptiness? And why does it whisper that everything we thought we knew about reality might be only 5% of the story? Get comfortable and settle in. Subscribe if you have not already, and stay with us tonight, because the trail that begins with a single wrong number in a cold, dark tunnel leads somewhere far stranger and far older than the machine that found it. Let us get into it. Part 1. The Machine That Holds the Big Bang. If you want to look back at the very dawn of creation, you do not look up at the stars, you look down. Deep beneath the quiet border between France and Switzerland, buried about 300 feet below the meadows and the cobblestone streets, there is a sleeping Leviathan. It is the most complex machine ever built by human hands, a cathedral of modern science, a ring of superconducting steel and wire 27 kilometers around, roughly 17 miles, that pushes the very limits of what engineering can do. This is the Large Hadron Collider, the machine we usually just call the LHC, built by CERN, the European Organization for Nuclear Research. And it is not really a laboratory in the way you might picture one. It is closer to a time machine. Its single purpose is to reach back and pull away the veil of reality, to carry us to a moment when the universe was less than a billionth of a second old. To touch the fires of creation, though, humanity first had to build the coldest place in the known universe. Come down there with me for a moment, in your mind. Step into the elevator at the surface, where the grass is ordinary and the sky is ordinary, and cows are grazing in fields that sit directly above one of the strangest machines ever built. The doors close, and you descend, 300 feet, past layers of rock that were laid down long before there were human beings to name them. When the doors open again, you are standing in a tunnel that curves away from you in both directions, so gently that you cannot see it bend, and yet you know that if you followed it, it would carry you in a great circle 17 miles around, and bring you back to exactly where you started. The walls are lined with a single continuous machine, blue and silver and impossibly clean, humming with a cold you can feel through your coat. There is no drama down here, no sparks, no noise of engines, just a long, patient quiet, and the knowledge that inside those pipes, protons are already circling faster than your mind can hold. It is one of the few places on Earth where you can stand still and be, in a real sense, right next to the beginning of time. To hold steady the storms raging inside this machine, the 17-mile tunnel is wrapped in an enormous cooling system. Liquid helium is pumped without rest through the veins of the collider, dragging the temperature of its huge superconducting magnets down to minus 271 degrees Celsius, which is only 1.9 degrees above absolute zero. Let that number settle for a moment, because it is stranger than it sounds. The empty void of interstellar space, far from the warmth of any star, sits at about 2.7 degrees above absolute zero. The inside of the LHC is literally colder than outer space. It is an artificial pocket of near-perfect stillness, engineered so that the electric currents feeding those magnets can flow without losing a single fraction of their strength to resistance. And this matters to you more than it might seem, because that impossible cold is the price of admission. Without it, none of what follows could happen at all. Within that freezing quiet, the real violence begins. The LHC is a racetrack built for the ultimate cosmic race. Scientists pull protons, the positively charged building blocks at the center of every atom, out of something as ordinary as a small bottle of hydrogen gas. These tiny specks of matter are injected into two ultra-high vacuum pipes running side by side, one beam traveling clockwise, the other counterclockwise. Then the magnets wake up. More than 9,000 superconducting magnets, some of them weighing as much as 35 tons each, act like an invisible whip made of pure magnetic force. They steer and they push these microscopic chariots faster and faster around the 27-kilometer track, all the way to the breaking point of physics itself. The protons climb until they are moving at 99.99991% of the speed of light. At that speed, a single proton loops the entire 17-mile underground ring more than 11,200 times every single second. They are moving so fast that time itself begins to stretch and slow around them, warping in exactly the way Albert Einstein predicted it would more than a century ago. But these protons are not meant to run forever. They are meant to crash. At 4 carefully engineered intersection points around the ring, the two beams are forced to cross. 40 million times every second, packets of protons slam into one another in head-on collisions. And when particles meet at almost the speed of light, they do not simply bounce apart, they shatter. The kinetic energy packed into that impact is so dense that for a sliver of a microsecond, the temperature at the collision point spikes to more than 100,000 times hotter than the core of the Sun. In that microscopic inferno, the ordinary rules of nature stop applying. Under normal conditions, quarks, the tiny particles that make up every proton, are locked together forever by gluons, the carrier particles of the strong nuclear force. They are held in a prison that, as far as everyday physics is concerned, can never be opened. But at temperatures of trillions of degrees, the prison melts. The protons melt. For the briefest instant, the quarks and the gluons are torn loose and set roaming freely, forming an exotic state of matter we call the quark-gluon plasma. It is not a solid, not a liquid, not a gas. It behaves like a perfect fluid, a primordial soup of almost pure energy that flows with very nearly zero friction. And here is the part that should make the back of your neck prickle. This perfect fluid has not existed anywhere in our universe for 13.8 billion years. The last time this plasma flowed freely, the entire cosmos was only about a millionth of a second old. So when scientists collide particles in the freezing depths beneath Geneva, they are, quite literally, holding a small piece of the Big Bang in the palm of a human hand. We're calling up the ghosts of creation and asking them our oldest questions. For a long time, we thought we already knew what those ghosts would say. We had a map, a flawless mathematical blueprint of reality that seemed to explain everything we found in the wreckage of these collisions. Every prediction it made came true. Every gap it left was eventually filled. It felt finished. But as the LHC pushed further and further into the unknown, the whispers coming back from the edge of the Big Bang slowly began to change. The numbers started very quietly to drift, and the perfect map that 50 years of physics had drawn was about to catch fire. Hold on to that image of the machine for a moment before we go on, because it is easy to hear all of this as abstraction, and it is anything but abstract. Somewhere under those green fields tonight, in the dark and the cold, that ring is still there. It is waiting. And the story of what it found in the empty space inside itself, the thing hiding in the quantum vacuum that made scientists check their instruments again and again before they dared to believe it, is the story we're going to follow all the way down. Part 2. The Fortress of the Standard Model. For 50 years, humanity built a fortress out of pure thought, and we called it the Standard Model of particle physics. It was never just a theory. It was an empire, one of the greatest achievements the human mind has ever produced, and it explained almost everything we could see, touch, or measure. To understand the crisis quietly unfolding in physics right now, you first have to understand how absolute, how impenetrable, this fortress once seemed. The Standard Model came together in the second half of the 20th century, assembled piece by the brightest minds across several generations. It took the endless complexity of the cosmos and reduced it to something almost unreasonably simple, a recipe both beautiful and terrifyingly precise. Imagine a cosmic periodic table, but instead of cataloguing chemical elements, it catalogues the smallest fragments of reality that exist. According to the Standard Model, everything that has ever existed is built from just 12 fundamental particles of matter, governed by 3 fundamental forces. The matter particles fall into 2 families, the quarks and the leptons. Quarks are the sociable builders. They bind together to form protons and neutrons, the heavy hearts of atoms. Leptons are the other family, and they include the familiar electron, the little particle that buzzes around the atomic nucleus and brings electricity, chemistry, and life itself into being. But particles alone cannot build a universe. They need rules. They need forces to tell them how to move, how to bind, and how to fall apart. The Standard Model names those forces and hands, each of them a messenger particle, a boson, whose whole job is to carry instructions between the particles of matter. The strong nuclear force, carried by gluons, works like a cosmic glue, holding the nucleus of an atom together against pressures that should tear it apart. The electromagnetic force, carried by photons, governs light and electricity and the magnetic fields that shield our planet, and the weak nuclear force, carried by particles called the W and Z bosons, runs the slow, silent alchemy of radioactive decay, the same process that fuels the fusion burning quietly in the core of our sun. For decades, every prediction this framework made was tested in laboratories and particle accelerators around the world, and every single time the Standard Model came back victorious. It predicted the existence of quarks before anyone had ever seen one. It predicted the masses of the W and Z bosons with astonishing accuracy. It was, by any honest measure, a flawless map of the quantum world. But there was one glaring, haunting empty space on that map. The equations worked perfectly, except for a single enormous contradiction. According to the raw mathematics, none of these particles should have any mass at all. They should all be racing through the universe at the speed of light, which would mean atoms could never form, stars could never ignite, and you and I could never exist. To fix that catastrophic flaw, the physicist Peter Higgs and several colleagues proposed a radical idea in the 1960s. They imagined an invisible field spread across the entire universe, a field that drags on certain particles as they move and in doing so gives them mass. The fingerprint of that field would be a new particle, the Higgs boson. Finding it became the holy grail of modern science. It was the ultimate test. If the Higgs did not exist, the entire Standard Model would collapse, taking 50 years of physics down with it. And that, more than anything else, is why the Large Hadron Collider was built in the first place. On the 4th of July 2012, the world watched as CERN made the single most important announcement in the history of particle physics. It is worth remembering the scene, because it was one of those rare days when a piece of pure mathematics stepped out into the daylight and became human. In a packed auditorium in Geneva, physicists who had spent their entire careers chasing this one particle sat shoulder to shoulder, some of them having flown in overnight, some having waited in line since before dawn for a seat. Among them, in the front rows, was Peter Higgs himself, an old man now, watching the confirmation of an idea he had first written down nearly half a century earlier. As a young researcher, no one was sure to believe. When the results appeared on the screen and the meaning of them settled over the room, he was seen to take off his glasses and wipe his eyes. Think about that. A single thought, held patiently for 50 years, finally answered by a machine 17 miles around, and the labour of thousands of people. That is what the Standard Model could do at its height. That is why its cracks would matter so much. Buried inside the data from trillions of collisions, they had found it. The Higgs boson was real. The final piece of the puzzle clicked into place, the Standard Model was complete, and the scientific community erupted in celebration. Nobel Prizes were awarded, and rightly so. But it is worth stopping to ask what it actually takes for physicists to claim a discovery like that, because their standard of proof is almost impossible to imagine. They do not rely on a hunch, or on a single strange reading. The empire of the Standard Model demands a level of certainty that exists almost nowhere else in human knowledge. In particle physics, a discovery has to clear a statistical threshold known as 5 sigma. In plain language, 5 sigma means that if the particle did not truly exist, there would be only about a 1 in 3.5 million chance that the data could have lined up, by pure luck, to look as if it did. Think about what that means. In much of biology, a 1 in 20 chance of being wrong is treated as a meaningful result. In medicine, a 1 in 1,000 chance of a false positive is considered highly rigorous. But fundamental physics demands something closer to perfection. It demands that the universe repeat its secret over and over, across billions of separate collision events, until every shadow of doubt has been burned away by sheer statistical light. That is the gold standard, and the Higgs boson cleared it cleanly, cementing the Standard Model as the most successful scientific theory ever devised. For a long time, I thought the discovery of the Higgs was the ending, the final chapter in the book of fundamental physics, the last brick in a finished cathedral. But it was not the end at all. It was the strange, quiet calm that comes right before a storm. With the Higgs confirmed, the map looked complete, and physicists expected the collider to simply keep confirming what they already knew, adding a few decimal places of precision to a masterpiece. Instead, as the machine ran at higher energies and gathered mountains of data no one had ever collected before, the universe began to whisper something deeply unsettling. The numbers began to drift. At first they were tiny whispers buried in the background noise, a fraction of a percent here, a slight deviation there, nothing anywhere close to a 5 sigma discovery, just isolated ghosts in the machine. But then the ghosts started to multiply, and the first of them, the one that forced the world to finally admit our understanding of reality was broken, came from one of the strangest and most short-lived fragments of matter ever studied. Part 3. The first crack in the wall. The first real crack in the authority of the Standard Model did not come from some blinding, world-shattering collision. It came from the quiet, patient study of one of the most unstable fragments of matter in the universe. Deep inside the Large Hadron Collider ring sits an experiment called LHC. Unlike the massive barrel-shaped detectors built to watch head-on impacts, LHCb is designed to catch the debris that sprays forward along the beamline in the instant after a collision. Its main job is to study a very specific and very strange particle, known as the beauty quark. In the sterile language of physics, its official name is the bottom quark, but many scientists prefer the older word, beauty, because this particle offers a nearly perfect window into the hidden symmetries of the cosmos. The beauty quark is heavy, roughly 4 times the mass of a proton, and because of that heaviness it is violently unstable. The moment it is born in the fiery aftermath of a proton collision, it survives for only a fraction of a trillionth of a second before it decays, shattering into a cascade of lighter, more stable particles. But it is precisely inside that microscopic window of decay that new physics can hide. According to quantum mechanics, when a heavy particle decays, it does not simply split apart like a cracked stone. It transforms, passing through intermediate states, often summoning virtual particles up out of the quantum vacuum for the briefest instant before they vanish again into nothing. And if there are undiscovered forces or unseen particles lurking in the dark corners of reality, their quiet influence would subtly change the way the beauty quark breaks apart, leaving a mathematical fingerprint behind in the wreckage. So the scientists at LHCb were not hunting for a new particle directly, they were hunting for a shadow. What they were actually measuring is a foundational principle of the Standard Model called lepton universality. To feel why it matters, you need to meet the strange family of particles called leptons. The most famous lepton is the electron, that tiny negatively charged speck that powers our civilization, forms chemical bonds, and makes up the outer shell of every atom in your body. But the electron has a heavier sibling, a particle called the muon. A muon is identical to an electron in almost every way you could name. It carries the exact same negative electric charge. It has the exact same quantum spin. The only difference in the entire universe is that the muon is about 207 times heavier, and under the strict, unyielding laws of the Standard Model, the fundamental forces are supposed to be completely blind to that difference in mass. The weak force and the electromagnetic force should interact with an electron in exactly the same way they interact with a muon. As far as the forces are concerned, the two particles are mathematical equals, so when a beauty quark decays, and its energy transforms into these lighter leptons, the laws of physics lay down a strict, unbreakable rule. The beauty quark should decay into electrons at exactly the same rate it decays into muons. The ratio must be a perfect 1-to-1. That is lepton universality. It is a central pillar of modern physics, a quiet mathematical promise that the fundamental forces of the universe do not play favourites. For years, the LHCb detector counted these tiny shattering events, 1 million decays, then 10 million, then 100 million. And as the data poured in and the supercomputers crunched the numbers, a disturbing pattern began to rise out of the background static. The universe was, in fact, playing favourites. The beauty quarks were not decaying equally. They were turning into electrons noticeably more often than they were turning into muons. At first, the researchers assumed it had to be a mistake, a glitch in the detector, a misaligned sensor, a flaw buried somewhere in the fiendishly complex algorithms used to filter out the noise. They spent years agonizing over it, recalibrating, retesting, trying desperately to find the error that would restore order to the standard model. But the anomaly refused to disappear. In fact, the more data they collected, the sharper and more defined the discrepancy became. Its statistical significance climbed past the 3 sigma mark, meaning there was only about a 1 in 1,000 chance that this was a random fluctuation. It was not yet the gold standard of a 5 sigma discovery, but it was a siren going off in the dark. Something invisible, something written in none of the textbooks, was reaching out of the quantum vacuum and interfering with the decay. It was pressing an unseen thumb onto the cosmic scale, either holding back the creation of muons or quietly encouraging the creation of electrons. There is something almost eerie about how the discovery arrived. Not with an explosion, not with a single dramatic reading, but with a slow, creeping suspicion that would not go away. Picture the researchers checking the same result for the 10th time, the 100th time, poring over calibration logs at 2 a.m, quietly hoping to find their own mistake. Because a mistake would be so much more comfortable than the alternative. Every physicist is trained to distrust a beautiful anomaly, because the history of science is littered with thrilling signals that turned out to be a loose cable or a warm sensor. So they did the honourable thing. They tried for years to make the ghost disappear, and the ghost refused. That is the moment a curiosity becomes a crisis, when the people who most want to explain something away find that they no longer can. If that data holds, the implications are staggering. It would mean our understanding of the fundamental forces is not just incomplete, but wrong in a deep way. It would imply the existence of a brand new 5th fundamental force of nature, carried by a particle no human being has ever seen. And theoretical physicists, being who they are, immediately began sketching blueprints for what that entity might be. Some proposed a heavy exotic particle called a Z-prime boson, a darker and much more massive cousin of the particles that already carry the weak nuclear force. This hypothetical force carrier would have a strange preference, treating different generations of leptons differently, and so explaining the unequal decay. Others suggested something even more radical, a particle called a leptoquark. A leptoquark would be an unprecedented bridge, an entity that lets quarks and leptons directly interact and transform into one another, a thing that would shatter the rigid wall between the 2 great families of matter that has stood for a century. You should feel the weight of that, because it reaches all the way up to you. The rule these scientists were testing, this promise that the forces do not play favourites, is one of the quiet assumptions holding up the entire structure of matter that makes a body and a brain and a night like this one. So the beauty quark anomaly stopped being a mathematical curiosity buried on a hard drive. It became a beacon, a signal that an enormous undiscovered continent of physics was waiting just beyond the edge of what our machines could reach. It proved that the standard model, for all its terrifying predictive power, was blind to some force that was actively shaping the microscopic architecture of reality. But the most chilling realization was still to come, because while the scientists in Europe wrestled with the strange behavior of the beauty quark, another team, thousands of miles away across the Atlantic, was about to detonate a bombshell of their own. They were looking at that heavier sibling, the muon, in a completely different way, and what they found would not just crack the standard model, it threatened to pull the whole fortress down to its foundations. Part 4. The muon that wobbled too fast. To prove that the strange behavior of the quantum world was not just a glitch inside one particular machine, scientists needed independent confirmation. They needed to test the laws of nature with a completely different method, a completely different machine, and a completely different particle. So they turned their full attention to the muon. We have already met the muon, the heavier sibling of the electron, identical in charge and spin but roughly 200 times more massive. Unlike the stable electrons that power our world, muons are fragile things. They do not sit quietly inside the atoms around us. They are born in the violent upper layers of Earth's atmosphere when high-energy cosmic rays from deep space slam into the air and trigger a cascading shower of subatomic debris. This rain of muons falls on the surface of the planet every second of every day. Right now, as you listen to this, dozens of invisible muons are passing straight through your body, moving at nearly the speed of a light before they decay harmlessly into lighter particles. You are at this very moment being gently rained on by the fallout of the cosmos, and you cannot feel a thing. Because of their particular mass and their quantum properties, muons behave like extraordinarily sensitive cosmic antennas. And this is where the story gets subtle, so let me slow down. In quantum mechanics, a particle is never truly alone. The empty space around it is not empty at all. It is a boiling, chaotic quantum vacuum where virtual particles constantly pop into and out of existence for the tiniest fractions of a second. As a muon travels, it is forever interacting with this invisible sea, absorbing and emitting these fleeting virtual particles. If the standard model is perfectly complete, then we should be able to predict exactly which virtual particles the muon feels, because we already know every particle that exists. But if there are undiscovered particles hiding out there, unseen forces we have never catalogued, they too would rise up out of the quantum vacuum and give the muon the faintest extra tug. The ultimate test of this idea was designed at Fermilab, the premier particle physics laboratory in the United States, sitting in the flat farmland just outside Chicago, Illinois. But to run the experiment, the scientists needed one very specific and very unusual piece of equipment, a perfectly circular, 50-foot wide superconducting electromagnet. And there was a problem. The only magnet capable of the necessary precision was located at Brookhaven National Laboratory in New York, nearly 1,000 miles away. You cannot simply take apart a magnet this delicate. It had to be moved in one piece, without bending or warping by even a fraction of a millimeter. So in the summer of 2013, that enormous ring was carefully loaded onto a specially built barge. It travelled down the east coast of the United States, around the tip of Florida, into the Gulf of Mexico, and then slowly up the Mississippi, Illinois, and Des Plaines rivers. Picture it for a moment. A giant, futuristic metal ring gliding silently past the American heartland on the water, drawing crowds along the riverbanks, all of it for the purpose of measuring a particle that exists for barely 2/millionths of a second. Once it was safely installed at Fermilab, the experiment, officially named muon G-2, finally began. The concept behind it is beautifully simple, even if the execution is almost unimaginably hard. Like any fundamental particle with an electric charge and a quantum spin, a muon behaves a little like a tiny compass needle. When you place it inside a powerful magnetic field, it does not just sit there. It spins, and as it spins, its internal magnetic axis wobbles, much the way a spinning top wobbles as it begins to slow. Physicists call this wobble magnetic precession. The rate at which the muon wobbles is set by a number known as the G factor. For a perfectly isolated particle, the mathematics of the early 20th century predicted this number should be exactly 2. But because the muon is constantly trading virtual particles with the quantum vacuum, its wobble is shifted just slightly by a microscopic amount. That tiny deviation away from the number 2 is what the experiment was built to measure. Theoretical physicists had already calculated exactly what the wobble should be, folding in every known particle and force in the standard model. Their prediction was precise to about 12 decimal places, making it one of the most rigorously calculated numbers in the entire history of human knowledge. The Fermilab machine then fired billions of muons into the perfectly uniform magnetic field of the Great Ring, watching the microscopic compass needles wobble and measuring their precession with a precision that is almost impossible to describe. For years, supercomputers analyzed the decay trajectories, filtering out the noise, narrowing the margin of error grain by grain. And in April of 2021, the Fermilab team was finally ready to show its findings to an anxious, waiting scientific world. Picture that morning for a second, because moments like it are rare in a human life. For years, the true answer had been hidden even from the scientists themselves, the crucial number deliberately shifted by a secret offset so that no one could nudge the result toward what they hoped to see. Hundreds of researchers gather on a video call that stretches across time zones and continents, coffee going cold on desks in Illinois and Italy and Japan. Someone shares their screen. A single line of code is about to remove the offset and reveal, for the first time, whether the universe agrees with the standard model or quietly breaks from it. There is a countdown. There is a held breath you can almost hear through the microphones, and then the true value appears on the screen, and it does not land where the theory said it should. Somewhere in that room of exhausted, elated people, you can feel the exact instant that a 50-year-old certainty begins to come apart. That feeling, that mixture of dread and joy at watching your own textbook fail, is what discovery actually looks like. When the data was unblinded, it sent a shockwave through the community. The muons were wobbling too fast. The measured magnetic moment did not match the immaculate prediction of the standard model. Something invisible, something massive and unknown, was rising out of the quantum vacuum and pulling on the muons, forcing them to precess faster than the laws of physics said they could. The gap between the theoretical prediction and the experimental reality reached a statistical significance of 4.2 sigma, meaning there was only about a 1 in 40,000 chance that the result was a fluke. It was not yet the 5 sigma gold standard on its own, but when you set it beside the glaring anomalies already showing up in the beauty quark experiments over at the Large Hadron Collider, the picture became impossible to ignore. The anomalies were not isolated, they were systemic. They were appearing in different particles in different machines on different continents. The Fermilab result was the devastating confirmation the European scientists had been waiting for. The standard model was failing. The quantum sea was swarming with unseen ghosts, whole new forces of nature or exotic particles that had deluded us for a century, and the invisible architecture of the universe was finally beginning to reveal itself. It was far more complex and far more mysterious than anyone had dared to imagine. Part 5. The impossible weight of the W boson. The anomalies of the beauty quark and the muon hinted at invisible forces operating out on the fringes of the standard model. But the next great fracture struck directly at its structural core, and to understand it, we have to turn away from the exotic for a moment and look at the force that literally powers the stars. Of the 4 fundamental forces of nature, the weak nuclear force is easily the most counterintuitive. Gravity pulls galaxies together. Electromagnetism binds atoms and creates light. But the weak force does not push or pull in the ordinary sense at all. Instead, it transforms. It is the ultimate cosmic alchemist, able to reach inside the nucleus of an atom and change the fundamental identity of a particle. When a star like our Sun burns, it leans on the weak force to begin nuclear fusion. The weak force triggers a process in which a down quark inside a neutron flips into an up quark, turning that neutron into a proton, and that tiny transmutation releases the boundless energy that bathes our planet in warmth and keeps every living thing alive. That is not a metaphor. The reason there is light in the sky at all traces back to this one strange force, quietly rewriting the identity of particles in the Sun's core. But forces do not act by magic. They need messengers to carry their instructions across the quantum void, and for the weak force, one of those messengers is a particle called the W boson. The W boson is a giant of the quantum world. It weighs nearly 80 times as much as a proton, and in the unforgiving realm of particle physics, all that mass comes at a catastrophic cost to stability. The moment a W boson comes into existence, it is essentially crushed by its own weight. It survives for only a fraction of a centillionth of a second before it violently decays into a lighter lepton, an electron or a muon, along with an invisible ghost particle called a neutrino. Because its lifespan is so unimaginably short, capturing and studying a W boson is one of the most agonizing challenges in all of science. You cannot trap it in a chamber. You cannot set it on a scale. The only way to determine its mass is to study the shattered debris it leaves behind after it decays, tracing the paths of the electrons and muons outward and working backward to calculate the energy of the particle that gave birth to them. This Herculean task was taken on by the Collider detector at Fermilab, the CDF collaboration, using the powerful Tevatron particle accelerator in Illinois. The researchers did not simply look at a handful of collisions. They committed to an obsessive campaign lasting roughly 4 decades, sifting through the wreckage of trillions of proton and antiproton collisions, carefully isolating more than 4 million individual W boson decay events. And to measure the mass of a fleeting particle, this precisely requires an understanding of your own equipment that borders on madness. The scientists had to account for the microscopic alignment of every sensor, the subtle fluctuations in the magnetic fields, and the precise behavior of millions of background particles that could distort the final answer. To keep any subconscious human bias from creeping in, they worked under a strict blinding protocol. The final number was hidden from them, locked away in an encrypted file for years, while they checked and rechecked their algorithms and calibrated their models against particles whose masses were already known. Finally, in the year 2022, the team agreed there was nothing left to check. The data was unblinded, the final algorithms were run, and the measured mass of the W boson was revealed. The Standard Model, using its rigid, perfectly balanced equations, predicted that the W boson should have a mass of about 80,357 mega-electron volts. But the Tevatron data told a different story. The CDF experiment measured the mass at 80,433 mega-electron volts. It was heavier than it was supposed to be. Now the difference might sound trivial, less than 0.1%. In many fields, a discrepancy that's small would be rounded away and dismissed as an artifact. But in the hyper-precise architecture of quantum physics, a deviation like this is the equivalent of a catastrophic earthquake. The equations of the Standard Model are not a set of isolated independent statements. They form a deeply entangled interconnected web called electroweak theory. The mass of the W boson is mathematically locked into a strict relationship with the mass of the Higgs boson and the mass of the heaviest known particle, the top quark. If the W boson is heavier than the equations allow, it means the entire mathematical framework holding the Standard Model together is out of balance. It means the theory we have trusted for 50 years is fundamentally incomplete, and the statistical weight of this particular measurement was devastating. The deviation from the Standard Model reached 7 sigma. Remember that 5 sigma is enough to claim a discovery and rewrite the textbooks. 7 sigma means there is less than a 1 in a trillion chance that the result is a random fluke. It is one of the most precise and definitive anomalies ever recorded in the history of science. To feel why so small a difference could carry so much weight, picture the Standard Model not as a list of separate facts, but as a single, tightly strung web. Pull on any one thread, and every other thread quivers in response. The mass of the W boson is not free to be whatever it likes. It is tied by the equations to the mass of the Higgs boson and to the mass of the top quark, the way 3 tuned strings on an instrument are locked into harmony with one another. For decades, when scientists measured all 3, they sang in tune, and that harmony was taken as one more proof that the theory was sound. So when the W boson came back heavier than the web allowed, it was not one wrong note in isolation. It was a sign that the whole instrument was subtly out of tune, that some unseen hand had been resting on the strings all along. And in physics, when the mathematics that has been right for 50 years suddenly cannot hold itself together, you do not blame the mathematics. You start looking, very carefully, for what you failed to include. Just like the muon wobbling too fast in its magnetic field, the unexpectedly heavy W boson points to unseen entities lurking in the quantum vacuum. The leading idea is that undiscovered, incredibly massive particles are flickering into existence for the briefest instants, interacting with the W boson and lending it a kind of phantom weight before vanishing back into the void. The Standard Model is blind to these interactions for the simplest possible reason. It does not know these new particles exist. The W boson mass shock proved, beyond any reasonable doubt, that the anomalies we are seeing are not scattered errors. They are the unmistakable signatures of a vastly more complex, unmapped universe. But as physicists scrambled to identify these new forces, they were forced to confront an even deeper and more unsettling mystery. Because the cracks in the Standard Model are not only about particles behaving badly, they point toward a flaw in our understanding of why anything in the universe exists at all. Part 6. The War That Made Us. Every anomaly we have followed so far, from the lopsided decay of the beauty quark to the wobble of the muon and the impossible weight of the W boson, points toward invisible particles and undiscovered forces hiding in the dark. But there is a far deeper and far more terrifying flaw in our physics, one so profound that it does not just ask how particles interact, it asks why anything exists at all. To face it, we have to leave the collisions in Geneva and Illinois behind and travel back 13.8 billion years to the absolute beginning of time. According to the foundational laws of quantum mechanics and relativity, pure energy can be converted into physical matter. That is the real meaning behind Einstein's famous equation, energy equals mass times the speed of light squared. In the blinding, unimaginable heat of the Big Bang, a point of infinite density exploded outward, releasing a shockwave of pure energy. As the young cosmos expanded and cooled, that boiling sea of energy began to condense into the first particles of matter. But there is a strict and terrifying rule governing how matter comes into being. The universe demands balance. Whenever energy turns into matter, it must create 2 perfectly opposing things at the same instant. For every particle of ordinary matter that is born, an exact twin of antimatter must be born alongside it. Antimatter is not science fiction. It is a very real, mathematically necessary counterpart to the physical world we know. An antiparticle has the exact same mass as its normal twin, but it carries the opposite electric charge and the opposite quantum properties. For every negatively charged electron born in the fires of creation, a positively charged positron had to appear. For every quark, an antiquark. So in the first millionth of a second of the universe, the cosmos was a violently balanced war zone, filled with exactly 50% matter and exactly 50% antimatter, and that perfect symmetry carries a deadly consequence. When a particle of matter and a particle of antimatter touch, they annihilate each other completely. They vanish in a flash of pure energy, leaving nothing behind but light. Hold that picture, because it is one of the most beautiful and merciless facts in all of physics. A particle and its opposite meet, and neither survives. There is no wreckage, no fragment, no compromise. Where there were two specks of matter, there is now only a pulse of light racing outward, and the accounts of the universe are balanced to the last decimal. Now multiply that meeting by every particle that existed in the first fraction of a second, an ocean of matter and an equal ocean of antimatter poured together in the same searing instant. The early universe should have been the most efficient act of destruction ever to occur, a flash of annihilation so total that it consumed itself and left the cosmos empty and bright and forever still. The fact that it did not, the fact that anything at all was left standing when the light died down, is the quiet miracle we're about to try to explain, and you are the evidence. So if the laws of physics as we understand them are truly absolute, the early universe should have been a very brief and very spectacular suicide. The equal oceans of matter and antimatter should have crashed together and annihilated again and again until every last particle was gone. The cosmos should have been left as an expanding, empty void filled with nothing but cold, ancient light. No atoms should have survived, no stars should have ignited, no galaxies should have formed, and you and I should absolutely not be here. But we are here. You're listening to this, made of solid, stable matter. The Earth beneath you, the sun in our sky, the billions of galaxies stretching across the observable universe, all of it is built exclusively from ordinary matter. Antimatter, for all practical purposes, has vanished from the cosmos. It shows up only fleetingly, in violent cosmic ray collisions or deep inside our particle accelerators, before it is instantly destroyed. The simple fact that you are alive right now is proof that something went catastrophically wrong with the perfect balance of the universe. In the great war between matter and antimatter, somehow matter won. The question is how? In 1964, two physicists named James Cronin and Val Fitch ran an experiment that stunned the scientific world and earned them the Nobel Prize. They found a microscopic flaw in the mirror of the universe, a phenomenon called charge parity violation, or CP violation. Until that moment, physicists believed that if you took a particle, swapped its charge to turn it into antimatter, and flipped its spatial coordinates as if looking at it in a mirror, the laws of physics would treat it exactly the same. But Cronin and Fitch discovered that the weak nuclear force, the same force behind the heavy W boson, occasionally breaks that rule. It does not treat matter and antimatter as perfect equals. There is a tiny asymmetry. During the boiling aftermath of the Big Bang, as matter and antimatter were locked in their apocalyptic war of mutual annihilation, this small CP violation tipped the scales. For every 1 billion particles of antimatter that were created, there were 1,000,000,001 particles of ordinary matter. It is a discrepancy so slight it almost defies comprehension. One extra particle of matter for every billion pairs that destroyed each other. Let me try to give that a shape you can hold. Imagine a cosmic scale, with 1 billion grains of sand piled on the left for antimatter, and 1,000,001 grains piled on the right for ordinary matter. When the annihilation swept through, it carried away 1 billion grains from each side, and the entire visible universe, every galaxy, every nebula, every black hole, and every human being who has ever lived, is built out of that single surviving grain of sand. As the universe expanded and cooled, the great annihilation raged until all the antimatter was gone. The overwhelming majority of the ordinary matter was destroyed right along with it. But because of that 1 in a billion asymmetry, a thin remainder of ordinary matter was left over, the ash of a cosmic war, and those survivors went on to build every star, every planet, and every living thing that exists today. We are the leftover, the tiny remainder of a nearly perfect self-destruction. Scientists eventually managed to fold CP violation into the equations of the Standard Model by studying certain neutral particles that were caught changing their identities. But here is where the fortress collapses again. When we use the Standard Model to calculate exactly how much CP violation the weak force can generate, the number that comes out is devastatingly small. The math tells us the asymmetry built into our current laws is billions of times too weak to explain why the universe survived. If the Standard Model were the whole truth, the tiny imbalance it allows would not have been nearly enough to save us. Matter and antimatter would have annihilated almost completely, leaving a universe with maybe one stray particle every few million light years. The fact that entire galaxies exist is glaring, undeniable proof that the Standard Model is missing an enormous piece of the puzzle. There must be some undiscovered, far more powerful source of CP violation hiding in the dark, some unknown particle or unmapped force that heavily favored the creation of ordinary matter in the first fraction of a second. Which means that we are living, breathing anomalies. Our very existence is a violation of the physics we currently understand. The ghosts we are chasing in our colliders are not just curiosities. They are the invisible architects that saved us from total erasure. And yet, even they are not the largest failure of the Standard Model. The biggest one is waiting for us not in a collider at all, but in the quiet turning of the galaxies overhead. Part 7. The Theory of the 5%. For all the microscopic anomalies we have hunted down inside our underground colliders, the most glaring failure of the Standard Model is not found by smashing particles together at all. It is found by stepping outside on a clear night and simply looking up. The Standard Model is a breathtakingly precise piece of mathematical architecture, and it perfectly unites three of the four fundamental forces. It explains the electromagnetism that lights our cities, the strong nuclear force that binds the cores of atoms, and the weak nuclear force that governs radioactive decay. But there is a fourth force, the very first one humanity ever noticed, the force that keeps your feet on the ground, shapes the orbits of planets, and crushes dying stars into black holes. It is gravity. And if you open up the master equations of the Standard Model and look for it, gravity is simply not there. It does not appear at all. Our understanding of gravity comes from an entirely separate framework, Einstein's theory of general relativity, which describes gravity not as a particle, but as the bending and curving of the fabric of space and time itself. General relativity works flawlessly on the largest cosmic scales, but when physicists try to shrink it down into the microscopic quantum realm, the mathematics falls apart, spitting out infinities and impossibilities. For nearly a century, the greatest minds in physics have tried to marry the quantum forces of the Standard Model to the gravity of general relativity, to build a single unified theory of everything. And for nearly a century they have failed. The Standard Model is blind to gravity, and because it is blind to gravity, it is blind to the true rulers of the cosmos. To feel the scale of our ignorance, we only need to look at the spinning disks of distant galaxies. In the 1970s, the astronomer Vera Rubin was studying the rotation of spiral galaxies, measuring how fast the stars at the outer edges were moving compared to the stars near the core. By the ordinary laws of physics, a galaxy should behave a bit like our solar system. The planets far from the Sun move more slowly than the planets close in, because the pull of gravity weakens with distance. So the stars at the outer edge of a galaxy should orbit far more slowly than the stars packed into the bright central core. But that is not what the telescopes showed. Rubin discovered that the stars at the outer edges were tearing through space at impossible velocities. They were moving so fast that the visible mass of the galaxy, all the glowing stars and gas clouds and dust, did not have anywhere near enough gravitational pull to hold them in orbit. By every known law of physics, these galaxies should have flung themselves apart, hurling their stars out into the freezing void between galaxies. Sit with how quietly world-changing that measurement was. Vera Rubin was not smashing anything, not building a machine the size of a city. She was pointing a telescope at the soft light of distant spiral galaxies and carefully measuring how fast their edges turned, night after patient night. And the numbers she wrote down did not match the universe as anyone understood it. Every spiral she looked at told the same impossible story. The outer stars were racing along as though held by a hand no one could see. She could have doubted her instruments. She could have quietly filed the result away. Instead, she trusted what the sky was telling her, and in doing so she revealed that the overwhelming majority of the universe is made of something we still cannot name. It is worth remembering when we talk about ghosts and singularities, that the first solid evidence for all of it came from a woman patiently watching starlight and refusing to look away from a number that did not add up. The only explanation that worked was that the galaxies were wrapped in an enormous invisible halo of some unknown material, a material that does not absorb light, does not reflect light, and does not interact with electromagnetism in any way. It makes itself known only through the brute pull of gravity. We call this phantom substance dark matter, and when astronomers calculated how much of it was needed to hold the spinning galaxies together, the numbers were staggering. Dark matter does not merely exist, it dominates. It outweighs all the visible matter in the universe by a ratio of more than 5-1. So the astronomers turned to the particle physicists and asked a simple question. Which particle in the Standard Model accounts for all of this invisible mass? The particle physicists checked their flawless 50-year-old map of reality, and they found nothing. Not a single particle in the Standard Model has the right properties to be dark matter. It is a complete unknown. The matter that makes up you, me, the Earth, and every star you can see in the night sky accounts for a mere 5% of the total mass and energy of the universe. The Standard Model is not a theory of everything. It is a theory of the 5%. We are adrift on a dark ocean, and we have mapped only the foam on the surface. But the nightmare does not end with dark matter. In the late 1990s, astronomers were studying the light from distant exploding stars, a particular kind called Type Ia supernovae, trying to measure how quickly the gravity of all the matter in the universe was slowing down the cosmic expansion that began with the Big Bang. They fully expected to find that the expansion was gradually decelerating, exhausted by the relentless inward pull of gravity. Instead, they found the exact opposite. The expansion of the universe is not slowing down, it is speeding up. Some mysterious repulsive force is actively pushing the fabric of space-time apart, driving the galaxies away from each other at ever-increasing speeds. We call this force dark energy, and it is the dominant thing in the cosmos, making up roughly 68% of everything. To explain dark energy, quantum physicists reached for the idea of vacuum energy, the built-in energy of empty space created by all those virtual particles constantly popping in and out of existence. They used the very best mathematics the Standard Model had to offer to calculate how much vacuum energy should fill the universe, and then they compared it to how much dark energy the astronomers actually measured. The result was the most humiliating failure in the history of science. The quantum prediction was larger than the observed reality by a factor of 10 to the power of 120. That is a 1 followed by 120 zeros. It is a mismatch so unfathomably vast that there are not enough atoms in the entire universe to write the number out. It is, without exaggeration, the worst prediction theoretical physics has ever made. So step back and look at what we are holding. The accelerating expansion of the universe, the presence of dark energy, and the overwhelming grip of dark matter together prove that our fundamental understanding of reality is deeply, structurally broken. The wobbling muons and the 2 heavy W bosons down in our colliders are not isolated glitches. They are the tiny ripples of these enormous invisible cosmic forces finally bleeding through into our instruments. The ghosts of the universe are beginning to make themselves known, and to capture them, physicists are being forced to propose particles and dimensions that sound less like science and more like something out of a dream. The 4 familiar pillars of reality are no longer enough to hold the sky up, which means there must be a 5th. Part 8. The 5th Force. For half a century, the laws of physics insisted that every interaction in the known universe, from the majestic orbit of galaxies to the quiet decay of a single radioactive atom, was governed by just 4 fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force were the bedrock of reality, the 4 pillars holding up the entire architecture of the cosmos. But the steady drumbeat of anomalies echoing out of the Large Hadron Collider and Fermilab has pushed the scientific community toward a conclusion that is both terrifying and exhilarating. 4 pillars are not enough. The wobbling of the muon, the impossible mass of the W boson, and the lopsided decay of the beauty quark all point toward the same earth-shaking possibility. There is a 5th fundamental force of nature, and this is not a flight of fancy. It is becoming a mathematical necessity, the thing required to stop the Standard Model from collapsing under the weight of its own contradictory data. But if a fifth force truly exists, we have to ask an obvious question. Why has humanity stayed completely blind to it for all of recorded history? The answer lies in the alien nature of the quantum realm. Gravity and electromagnetism stretch their invisible hands across millions of light years to shape the cosmos. This new fifth force plays by entirely different rules. It is most likely confined to distances so unimaginably small that it can only reveal itself when we smash particles together at velocities near the speed of light, and it appears to be extraordinarily selective. It does not interact with the ordinary matter that makes up you, me, and the world around us. It is a ghost force, waiting in the dark, only stirring when the heaviest and most unstable particles in the universe are violently ripped apart. And here is why a thing so shy, so hidden, so seemingly irrelevant to daily life should matter to you at all. The four forces we already know wrote the entire story of your existence. Gravity gathered the gas that became the sun. The strong force lit its core. Electromagnetism carried that light across 93 million miles of empty space to warm the surface of the Earth and to power every chemical reaction inside every cell of your body. If there is a fifth force, then our account of how reality is put together has a whole missing chapter, a set of rules that has been shaping matter from the very first instant, and that we simply never noticed. It may have helped decide why there is matter at all, why the universe is not empty. Finding it would not just add a line to a textbook. It would mean that the ground we have always been standing on has one more layer beneath it than we ever suspected, and that the world is stranger and more finely made than the confident maps of the last century ever admitted. But forces do not act by magic. In the strict framework of quantum mechanics, every force needs a messenger, a physical particle whose only purpose is to carry instructions from one point in space to another. If there is a fifth force, there must be a new, undiscovered force-carrying particle, and theoretical physicists are now locked in a desperate race to identify that unseen messenger, drafting blueprints for exotic entities that push the very limits of imagination. The leading candidate in this theoretical arms race is a massive hypothetical particle called the Z-prime boson. To understand it, we have to look at its established cousin, the ordinary Z boson, one of the known carriers of the weak nuclear force. The standard Z boson interacts with all particles equally, respecting that sacred rule of lepton universality. But the Z-prime boson would be a darker, heavier, and far more chaotic thing. If it exists, it carries a strange mathematical bias, treating electrons differently from muons. When a heavy beauty quark decays in the fiery aftermath of a collision, the Z-prime boson would rise up out of the quantum vacuum for a fraction of a nanosecond, tilting the outcome before vanishing back into the void. That single invisible interference would neatly explain why the LHCb experiment kept seeing beauty quarks decay into electrons far more often than into muons. The Z-prime boson would be a microscopic thumb on the cosmic scale, quietly leaning on the balance of nature. But as compelling as the Z-prime boson is, another group of physicists is proposing something even more radical, a particle they call the leptoquark. To feel why the leptoquark is so unsettling, you have to remember that for 100 years, particle physics has been rigidly divided into two families. There are quarks, the heavy particles that build the nuclei of atoms, and there are leptons, the lighter particles like electrons and muons that orbit them. These two families are separated by what has always looked like an absolute impenetrable wall. A quark cannot simply turn into a lepton. The fundamental laws of classification forbid it. But the leptoquark is a bridge particle, a theoretical monster that would carry the properties of both a quark and a lepton at the same time. If leptoquarks exist, they would shatter that wall, letting quarks and leptons interact directly, passing energy and identity back and forth in a microscopic dance the standard model flatly forbids. When a beauty quark shatters, a leptoquark could briefly form in the wreckage, forcing the decay to favour electrons over muons. The existence of such a particle would force us to rewrite every textbook on particle physics, because it would mean the neat categories of matter we have leaned on for a century are, at bottom, an illusion, a surface over some deeper and more profound symmetry in which all matter is quietly connected. And if that turned out to be true, it would be one of those rare ideas that is unsettling and beautiful at the same time. For a century we have sorted the universe into tidy boxes, the builders in one and the wanderers in another, quarks here and leptons there, never touching, never trading places. It is a comforting arrangement. the kind of order that makes reality feel knowable. The leptoquark would quietly erase the line between the boxes and suggest that the separation we took for a law of nature was only a habit of a cooled-down universe, and that in the fierce heat of the beginning, everything was once part of a single family, freely turning into everything else. The wall we thought was permanent would turn out to have a door in it, and the anomalies in the collider might be nothing less than the faint draft coming through that door, felt for the first time, and this is the strange comfort buried inside the crisis. Whether the ghost in our machines turns out to be the biased Z-prime boson, the rule-breaking leptoquark, or an entirely new class of physics we have not yet even imagined, one thing is certain. The age of the Standard Model, as a complete and final story, is over. We have reached the very edge of the map drawn by the physicists of the 20th century, and beyond it the water is uncharted and dangerous. But the discovery of a fifth force would not only solve the anomalies of the collider, it would hand us a new tool, a new lens through which to finally look at the darkest mysteries of the cosmos. Because to answer the ultimate riddles, the nature of dark matter, and the survival of the universe after the Big Bang, we have to look beyond the particles we already know and dive into the strangest and most elusive entities ever theorized. And the first of those ghosts is a particle so faint, so nearly untouchable, that when it was first proposed, even the man who dreamed it up was ashamed of what he had done. Part 9. The Ghost with No Mass. Long before the beauty quark decayed unevenly, and long before the muon wobbled out of line, there was the original ghost of the quantum realm. To find the ultimate answer to dark matter and the survival of the universe, we have to look at a particle so elusive it borders on the supernatural. We have to look at the neutrino. When the neutrino was first proposed in the 1930s by the physicist Wolfgang Pauli, it was an act of near desperation. Pauli was trying to explain some missing energy in a type of radioactive decay, and to make his equations balance, he invented a microscopic thief, a particle with no electric charge and, according to the Standard Model, no mass at all. He famously wrote that he had done a terrible thing, proposing a particle that could never be detected. For decades, the neutrino was exactly that, a phantom. Because it carries no charge and supposedly no mass, it is immune to the electromagnetic force and the strong nuclear force. It interacts with the world almost exclusively through the weak nuclear force, which operates over distances smaller than the nucleus of an atom. Because of this, neutrinos pass through solid matter as if it were not there. Right now, as you breathe, trillions of neutrinos forged in the nuclear furnace of the sun are streaming through your body at nearly the speed of light. They pass through you, through the earth, out the other side, and on into the infinite dark completely unimpeded, as though you were made of empty space. Stop and really picture that, because it is one of those facts that quietly rearranges your sense of your own body. As you lie here listening, a flood of these particles is streaming through you at this exact instant. Born 8 minutes ago in the heart of the sun, and not one in many trillions will so much as brush against a single atom of you on its way through. You are, to a neutrino, less solid than a pane of glass is to sunlight. The floor beneath you, the entire mass of the planet, the iron core nearly 4,000 miles down, all of it is essentially transparent to these ghosts. They are the closest thing nature has to a particle that is truly there and truly not there at the same time, and the fact that we managed to catch them at all, to prove they even exist and then to watch them change their identity in mid-flight, is one of the most delicate feats of listening our species has ever performed. But in the late 1990s, this ghostly particle delivered the very first fatal blow to the absolute authority of the Standard Model. Deep beneath a mountain in Japan, inside a massive underground tank of ultra-pure water called the Super Kamiokande detector, scientists were studying neutrinos raining down from the atmosphere and pouring out of the sun. The Standard Model said there were 3 distinct types, or flavors, of neutrino: the electron neutrino, the muon neutrino, and the tau neutrino. And because the model insisted they had exactly zero mass, they should travel through space locked forever in their original identity. But the Japanese detector revealed something impossible. The neutrinos were shape-shifting. As they travelled, they were spontaneously oscillating, morphing from one flavour into another, and here is the subtle, beautiful catch. In the strict laws of quantum mechanics, a particle can only experience the passage of time, and therefore only change or oscillate, if it is moving slower than the absolute speed of light. And anything moving slower than light must carry mass. The discovery of neutrino oscillation proved that neutrinos have a tiny, almost infinitely small mass. It was a genuine shockwave. The standard model was wrong, and it had to be hastily patched to account for this impossible weight. But that discovery created a new and agonizing problem. When astronomers realized the universe was buckling under the weight of invisible dark matter, they immediately pointed at the newly massive neutrinos. After all, neutrinos are invisible. They are everywhere, and now we knew they had mass. Could the trillions of them drifting through space be the dark matter holding the galaxies together? The supercomputers crunched the numbers, and the answer was a devastating no. Because neutrinos are so incredibly light and move so incredibly fast, they form what astrophysicists call hot dark matter. And if the universe were held together by hot, fast-moving particles, galaxies could never have formed in the first place. The gravity of the cosmos requires cold, slow, heavy dark matter, something that can clump together and act as the gravitational scaffolding on which stars are built. The three known flavors of neutrino were simply too light, too frantic to save the universe. So the theorists proposed a monster. They imagined a fourth kind of neutrino, a particle written nowhere in the standard model called the sterile neutrino. The sterile neutrino would be a heavyweight, far more massive than its three siblings. But what makes it truly strange is its isolation. The ordinary neutrinos at least feel the weak nuclear force. The sterile neutrino would be blind even to that. It would be severed almost completely from the quantum forces of the universe, reaching out to the cosmos through one force and one force only: gravity. And if sterile neutrinos exist, they would solve the deepest mysteries of astrophysics at a single stroke. Because they are heavy and interact only through gravity, clouds of them would pool around galaxies, providing exactly the invisible glue we observe as dark matter. And in the chaotic first microsecond of the Big Bang, heavy decaying sterile neutrinos could have supplied that missing surge of CP violation, the extra imbalance needed to wipe out the antimatter and let ordinary matter survive. They would be the ultimate mathematical savior, solving two of the largest problems in physics with one unseen particle. But how do you detect something that interacts only through gravity? You cannot catch it in a detector. You can only look for what is missing. When the beams inside the Large Hadron Collider smash together at nearly the speed of light, supercomputers carefully add up the total energy of the incoming protons and compare it to the total energy of the shattered debris. The fundamental law is that energy cannot be created or destroyed. What goes in must equal what comes out. But every so often, the detectors register a massive, inexplicable deficit. A chunk of energy simply vanishes from the collision point. And the question of where it goes has breathed life into the most radical, mind-bending theory in modern physics: string theory. For decades, string theorists have argued that the mathematics of our universe simply refuses to work in ordinary three-dimensional space. To unite the quantum world with gravity, the equations demand the existence of at least 10 spatial dimensions. According to this idea, the reality we experience, 3 dimensions of space and 1 of time, is only a thin slice of a much larger and stranger structure. We would be trapped on a kind of membrane, which physicists call a brane, floating inside a higher dimensional space known as the bulk. Every particle we know, the quarks, the electrons, the photons of light, would be permanently glued to our 3-dimensional brane. We cannot see the extra dimensions because the very light we see with is trapped in our own. But there is one force that is not trapped: gravity. In string theory, the messenger of gravity, a particle called the graviton, takes the form of a closed loop of vibrating string, and because it is a closed loop, it is not anchored to our brain. It can drift away. It can leak into the higher dimensions. This would elegantly explain why gravity feels so absurdly weak compared to the other forces. It would not be weak at all. We would simply be feeling a fraction of its true strength, while the rest of its power bleeds out into dimensions our senses can never reach. So when the Large Hadron Collider smashes particles together and records that missing energy, we may not just be watching the birth of an invisible sterile neutrino. We may be watching gravitons being flung clean out of our universe. We may be watching raw energy punch a hole through the fabric of reality and bleed out into a 4th, or 5th, or 6th dimension. The cracks in the standard model would no longer be mathematical errors at all. They would be the tearing of a veil. And that thought should stay with you, because it means the dark space just beyond your fingertips may not be empty in the way it looks. It may be a doorway. We are standing on the edge of a revolution that could shatter our understanding of existence, and the ghosts in our machines are whispering about hidden worlds and phantom forces and extra dimensions, folded up just millimeters from our eyes. Part 10. The Death of Symmetry. For decades, theoretical physicists held on to a beautiful, elegant dream. As the cracks in the Standard Model began to widen, they believed they already had the perfect mathematical mortar to seal them. That dream was called supersymmetry. Before the Large Hadron Collider ever fired its first proton, many of the greatest minds in physics were confident the machine would discover a hidden, perfectly balanced mirror world of particles. Supersymmetry offered a breathtakingly simple answer to the chaos of the quantum realm. It suggested that every particle we know of has a heavier, invisible twin, a superpartner. If those superpartners existed, they would solve the deepest mysteries all at once. They would provide a perfect candidate for dark matter. They would stabilize the mass of the Higgs boson, and they would restore a deep mathematical beauty to the fundamental equations of reality. It was a theory so elegant, so mathematically satisfying, that physicists assumed nature simply had to use it. But nature, it turns out, does not care about our sense of elegance. When the Large Hadron Collider was powered up to its maximum energy, shattering protons at unprecedented speeds, physicists waited for the superpartners to emerge from the wreckage. They waited for years. They sifted through the debris of quadrillions of collisions, and the superpartners never appeared. Not a single one. That devastating absence has forced the scientific community into a humbling realization. We may be watching the slow, quiet death of supersymmetry. The failure to find those elegant solutions suggests that the universe is far more chaotic, more asymmetrical, and more unpredictable than we ever wanted to believe. We are being asked to give up the comforting symmetry of our own mathematics and face a reality that is, at bottom, untidy. And that realization has triggered one of the most profound philosophical debates in the history of science. If the laws of physics are not a perfectly balanced masterpiece, then we have to ask a genuinely disturbing question. Are the laws of the Standard Model actually universal at all? For centuries, humanity operated on the assumption that the fundamental rules of nature are absolute. We believed that an electron here on Earth behaves exactly like an electron in a galaxy 10 billion light-years away. We believed the mass of the W boson and the strength of the weak force were fixed constants, carved into the very foundation of existence. But as the anomalies multiply, a radical new perspective is taking hold. What if the physics we measure in our laboratories is not a universal law, but only a local approximation? What if the Standard Model is just the local weather in our particular corner of reality? This carries us to the edge of mainstream science, out toward the staggering idea of the quantum multiverse. String theory and modern cosmology both hint that our universe might be just one expanding bubble in an endless boiling ocean of other universes. And in that multiverse, the fundamental constants of nature would not be fixed. They would be randomized. In another universe, gravity might be billions of times stronger, instantly crushing every newborn star into a black hole. In another, the electromagnetic force might be too weak to hold atoms together, leaving nothing but a thin drift of lonely particles. But in our specific universe, the laws happen to settle into a strange, finely tuned configuration that just so happens to allow carbon to form, stars to ignite, and life to evolve. We would be measuring these particular laws not because they are inevitable, but simply because we could not exist in a universe where the rules were any different. We would be trapped in a fragile local pocket of reality, mistaking our own address for the whole city. To truly know whether we live in a multiverse, or whether there is some deeper unifying theory waiting to explain every anomaly, we have to push far beyond the limits of our current technology. The Large Hadron Collider has been a magnificent machine. It found the Higgs boson, and it exposed the first fatal cracks in the Standard Model. But it has reached the ceiling of its power. The ghosts hiding in the quantum vacuum are too heavy, too elusive, and too energetic for it to catch. And so, after decades of discovery, the great machine is being wound down toward its long shutdowns, its beams going quiet while engineers rebuild it, and while the world argues over what should come next. To capture the particles responsible for dark matter, to isolate the fifth force, to finally chart the dark sectors of the universe, humanity would have to build a new cathedral of science. We would have to build the ultimate time machine. Deep in the planning rooms of CERN, the blueprints for that machine have already been drawn. It is called the Future Circular Collider. If it is approved and funded, it would dwarf the Large Hadron Collider in every way. The current ring is 27 kilometers around. The future circular collider would be a staggering 100 kilometers in circumference, requiring an enormous circular tunnel carved beneath the city of Geneva, passing under Lake Geneva and boring deep into the bedrock of the French Alps. To power this Leviathan, engineers would have to invent an entirely new generation of superconducting magnets, able to generate fields so intense they push the limits of material science. The machine would smash particles together with an energy at least 7 times greater than the current collider, creating microscopic fireballs that mimic the state of the universe fractions of an instant closer to the very moment of creation. But this ambition comes at a staggering cost. The estimated price of the future circular collider is around $20 billion, and the timeline is even more daunting. Even if the world's governments aligned to fund it today, the tunnel would not be finished until the mid-2040s, and the machine would not begin its highest energy collisions until the 2070s. We're talking about a project so vast that the physicists drafting its blueprints today know, with quiet certainty, that they will likely not live to see it completed. They are designing a machine for their students, and for their students' students. It is a multi-generational act of faith in the pursuit of truth. There is a kind of quiet heroism in that which is easy to miss. Imagine devoting your working life to laying the foundation of a cathedral you already know you will never see finished, drawing careful blueprints for a machine that will only switch on decades after you're gone, trusting strangers not yet born to carry the work the rest of the way. The people who built the great cathedrals of stone understood this. They cut and set the first stones knowing the spire would be raised by grandchildren they would never meet. The physicists sketching the future circular collider today are doing something very similar, only their cathedral is aimed not at the heavens above but at the first instant of everything, and they are doing it not out of certainty that it will pay off, but out of something more honest and more human than certainty, the simple refusal to stop asking. And you might reasonably ask why. Why pour billions of dollars and decades of human life into chasing invisible ghosts in the quantum void? Because the alternative is to stop. The alternative is to accept a broken map, to look up at the stars and to admit that we will never understand 95% of the cosmos. Humanity has never once accepted that kind of ignorance, and as it happens, the search for those ghosts is about to lead us somewhere no collider can reach, back to the first instant of time and to a kind of monster we had almost forgotten to look for. Part 11. The Wrong Kind of Ghost. When you step outside on a clear, cold night and gaze up at the sprawling architecture of the Milky Way, you are falling for the greatest optical illusion in human history. You might think you're looking at the universe in all its glory. You are not. Every glowing star, every swirling nebula, every planet and every living thing on Earth combined, all of it adds up to a mere 5% of the actual cosmos. The overwhelming majority of the universe is invisible, untouchable, and utterly silent. And for decades the brightest minds on the planet were certain they knew what it was made of. They believed dark matter was simply a new, undiscovered kind of subatomic particle. They called them WIMPs, weakly interacting massive particles. The theory was beautiful, elegant, and mathematically clean. It suggested that trillions of these microscopic phantoms were passing through your body, through the walls of your house, and through the core of the Earth every second, completely undetected. And to catch these ghosts, scientists launched one of the most ambitious and expensive engineering crusades in history. They retreated deep underground, beneath the towering peaks of the Gran Sasso Mountain in Italy, and down inside abandoned gold mines in South Dakota. They built heavily fortified subterranean laboratories, going that deep to shield their delicate instruments from the constant rain of cosmic rays. Inside these buried bunkers, they constructed enormous pristine tanks filled with ultra-pure liquid xenon, chilled to freezing temperatures. The plan was almost childishly simple and yet breathtakingly precise. They would sit in the dark watching the liquid xenon, hoping that just one single WIMP, out of the trillions passing through the Earth, would happen to crash into a xenon atom and produce a microscopic flash of light. They built the most sensitive radiation detectors in the history of civilization, and then they waited in the silent depths of the Earth. They waited for years. Years slowly stretched into decades. They kept upgrading the machines, making them larger, colder, more sensitive, filtering out every conceivable source of background noise until those xenon tanks were the quietest, most undisturbed places in the entire solar system. And still they waited. But the flash of light never came. Imagine for a moment that you're down there in one of those laboratories, a mile of solid rock pressing overhead. The elevator ride to the surface a full 10 minutes long. The air is cool and still and faintly metallic. In front of you sits a great steel tank taller than a house, filled with a ton of liquid xenon so pure it has been scrubbed of nearly every stray atom that does not belong. Ringing it are thousands of light detectors, each one poised to register a single photon, a single spark, the faintest possible signature of a collision that theory promised would eventually come. And your entire job, year after year, is to sit in that hush and watch for a flash that has been predicted for half a century. You watch through the seasons. You watch as the graduate students who started with you finish their degrees and move away. You watch as newer, larger tanks are built around the old ones, each one 100 times more sensitive than the last, and the tank stays dark. There is a particular kind of courage in that, in devoting a career to listening for a knock that may never come, and it is worth honouring even as we admit what the silence was quietly telling us. The great underground hunt was a catastrophic failure. Millions of dollars and the entire careers of brilliant physicists were swallowed by an unrelenting silence. The most advanced detectors on Earth returned absolutely nothing. The WIMP theory, the elegant mathematical dream that had sustained the physics community for half a century, was slowly bleeding to death. We had assumed the missing mass of the universe had to be a microscopic particle. We spent 40 years digging into the Earth to find it, and we found nothing at all. But as the detectors failed, one after another, a profound and unsettling thought began to ripple through the community. What if the fundamental assumption was wrong from the very start? What if dark matter is not a new exotic particle at all? What if it is not something microscopic we need to catch in a vat of freezing liquid, but something else entirely? And so, in a kind of desperate bid to save our picture of reality, theoretical physicists have begun abandoning the particle hunt and returning to a radical, almost heretical idea, one first proposed by Stephen Hawking and Yakov Zeldovich back in the 1970s. They have turned their gaze away from the tiny quantum world and toward the most violent and ancient entities ever forged by the cosmos. They have started hunting for the ultimate cosmic predator. Because if dark matter is not a particle, then the only other candidate capable of generating that much invisible gravity is a black hole. But not the kind of black hole you are picturing. When you hear the words black hole, you instinctively imagine a dying star, a sun millions of times larger than our own, running out of fuel, collapsing under its own crushing weight, and detonating in a spectacular supernova, leaving behind a singularity that devours everything nearby. Those are stellar mass black holes, and they are terrifying, but they are also relatively young. They could only be born after the first generations of stars had ignited, lived, and died. And here is the problem. The dark matter we observe has been there since the very beginning, acting as the gravitational seed that pulled the first galaxies together. Stellar black holes cannot be that dark matter, because they simply did not exist early enough to do the heavy lifting of galaxy formation. Which is where the story shifts from the massive to the microscopic, and from the death of a star to the very first fraction of a second of time itself. Long before there were stars to collapse, long before there were galaxies, long before the universe was anything more than a blindingly hot soup of pure energy, a different breed of monster may have been born. These are the primordial black holes. They are not the corpses of dead stars. They are the fossilized scars of the Big Bang itself, forged at a time when the universe was so dense, so hot, and so violent that the very laws of physics were nearly unrecognizable. And the answer to the greatest mystery of the cosmos may not be a gentle particle drifting through the dark, but a swarm of ancient invisible singularities that have been silently stalking the universe for 13.8 billion years. It is worth sitting with how large a reversal that is. For half a century, the picture of dark matter in nearly every classroom and documentary was soft and almost soothing, a fine invisible dust, a gentle fog of particles too shy to touch us, drifting harmlessly through everything. And now a growing number of serious physicists are asking whether that fog might instead be a scattering of the most extreme objects the universe has ever produced, points of collapsed space-time older than the first atom, each one a place where the ordinary rules simply stop. The missing mass would not be a whisper. It would be a graveyard of tiny monsters. Nothing about the night sky would look different. The galaxies would turn exactly as they do now. But the thing holding them together would have changed in our understanding, from the gentlest imaginable substance to the fiercest, and that shift tells you something about how little we truly know about the 95% of the universe we cannot see. To understand how such monsters were born, we have to travel back to that first microsecond of creation, to a moment when the entire universe was a boiling crucible of infinite pressure. And once you understand what happened there, the empty space between the stars will never look empty again. Part 12. Fossils of the Big Bang. To truly grasp what a primordial black hole is, you have to discard almost everything you have ever been taught about how gravity makes one. In the universe today, if you want to build a black hole, you need the mass of at least 3 suns to force matter to collapse against the outward pressure of nuclear fusion and quantum mechanics. The modern cosmos is simply too cold and too empty to create a singularity any other way. But the first instant of the Big Bang was a completely different realm. The universe was not empty. It was compressed into a space smaller than a single atom, containing all the energy that would ever exist, an environment of absolute unimaginable extremes. In that primordial furnace, you did not need a dying star to make a black hole. You only needed a tiny, fleeting imperfection. Most people picture the Big Bang as a perfect, smooth explosion, a flawless sphere of expanding energy inflating evenly in every direction. But the universe has never been perfect. It has always been chaotic, governed by the jittery, unpredictable laws of quantum mechanics. Down in the realm of the very small, energy and matter are never truly still. They are forever bubbling, shifting, and fluctuating in a boiling quantum sea. This microscopic chaos is what physicists call a quantum fluctuation. Now imagine taking that microscopic bubbling and stretching it across the entire cosmos in an instant. During the first billionth of a trillionth of a second after the Big Bang, the universe underwent a period of terrifyingly rapid expansion called cosmic inflation. As space expanded faster than the speed of light, it seized those tiny quantum ripples and froze them into the very fabric of reality. Because of those frozen ripples, the early universe was not a smooth, even plasma. It was lumpy. There were regions where the primordial soup of energy was slightly thinner, and regions where it was overwhelmingly, crushingly dense. I want you to try to feel the physical conditions of that single microsecond. The temperature was measured not in degrees but in trillions of degrees, a heat so absolute that atoms could not even begin to form. The universe was a boiling plasma of pure quarks and gluons, and the pressure was beyond human comprehension. In those hyperdense regions carved out by the quantum fluctuations, matter was packed so tightly that gravity began to assert its ultimate dominance. In the modern universe, when a great cloud of matter collapses, it forms a star, and the outward pressure of fusion halts the fall. But in the first microsecond, there were no atoms to fuse and no light to push back. There was only raw, unadulterated mass and the tightening grip of gravity, and the pressure was so immense that in those densest pockets, matter simply gave up. It did not ignite into a star. It did not swirl into a cloud. It collapsed directly inward, tearing a microscopic hole in the fabric of space-time. Try, just for a heartbeat, to stand inside that first microsecond, though nothing that could ever be called standing would survive there. There is no up and no down, no space to speak of, only a searing white density stretching in every direction, hotter than the core of any star that will ever form, pressed together more tightly than anything you have words for. There is no darkness yet, because light itself cannot travel more than the tiniest distance before it is swallowed again, and everywhere around you the fabric of reality is trembling, bubbling with those quantum ripples, some regions a shade thinner, some a shade denser. In one of the denser knots the pressure crosses an invisible line, and reality simply folds. A pocket of the young universe pinches shut and drops out of sight, leaving behind a scar that will still be drifting through the cosmos when the last star has died. It happens without sound, without warning, in less time than it takes a thought to form, and it happens, perhaps, billions upon billions of times. Let us pause to understand what a singularity actually is, especially one born in the fires of the Big Bang. A singularity is not a physical object the way a planet or a star is. It is closer to a mathematical breakdown, a point where matter has been crushed to zero volume, driving its density toward infinity. In the modern era, reaching that infinite density requires the agonizing death of a supergiant star to overcome the fundamental forces of nature. But in the primordial universe, the entire cosmos was already hovering on the razor's edge of infinite density. The quantum fluctuations were simply the gentle nudge that pushed those localized regions over the edge into oblivion. And this rapid cooling meant the window of opportunity was incredibly short. It lasted only a microscopic fraction of a single second. But in that infinitesimally brief window, an unimaginable number of singularities may have been forged. Think of bubbles forming in a pot of boiling water, except instead of pockets of air, these were pockets of infinite gravity. In an instant, billions upon billions of hyperdense pockets could have crushed themselves out of existence, leaving behind only their gravitational footprint. They were born in a swarm, a plague of microscopic gravity wells popping into existence throughout the expanding plasma. And unlike stellar black holes, which are strictly limited in size by the physics of dying stars, these primordial entities had no such limits. The size of a primordial black hole was set purely by the size of the quantum fluctuation that birthed it. Some were incredibly small, born from tiny ripples of overdensity. Others were monstrous, forged in enormous gravitational vortexes. They were the very first structures ever to exist. They predate the first atoms. They predate the cosmic microwave background. They are quite literally older than light itself. When the universe finally cooled enough for light to travel freely, when the blinding fog of plasma lifted and space became transparent, these ancient monsters were already there, waiting in the dark. Now here is where the mathematics turns genuinely disorienting. According to Einstein's theory of general relativity, absolutely anything can become a black hole if you compress it tightly enough. Every object with mass has a specific boundary of compression, a threshold called the Schwarzschild radius. If you took the Earth, with all its oceans, continents, and molten iron core, and somehow crushed all of that mass down to the size of a peanut, its gravity would become so intense that light itself could not escape, and the Earth would instantly become a black hole. If you wanted to turn the Moon into a black hole, you would have to crush it down to the size of a single grain of sand. In the cold, empty modern universe, there is no natural mechanism capable of that kind of pinpoint pressure. But the early universe was a realm of infinite pressure, and the primordial black holes forged there were not limited by the mass of a dying star. They were limited only by the size of the density spikes that made them. So primordial black holes can exist at almost any mass and any size imaginable. They shatter our ordinary sense of scale. One could have formed with the exact mass of the planet Jupiter, but compressed into a sphere no larger than an apple. More unsettling still, they could be far smaller than that. Picture Mount Everest, the heaviest mountain on Earth, billions of tons of solid rock and ice. In the crucible of the early cosmos, a primordial black hole could have been forged with the exact mass of Mount Everest, crushed down to a size smaller than a single proton. The weight of a mountain folded into something smaller than an atom. And this mind-bending distortion of size and mass is exactly what you need to solve the mystery of dark matter. Astronomers know that the dark matter holding the Milky Way together is not concentrated in the bright galactic disk where the stars live. Instead, it forms a huge, invisible, spherical halo that engulfs the entire galaxy, reaching hundreds of thousands of light-years out into the void. If that halo were made of giant stellar black holes, we would have seen their effects by now, watching them shred stars and light up with glowing accretion disks. But we see none of that chaos. The dark halo is silent, and that silence fits perfectly with a swarm of microscopic primordial black holes. Because their physical size is so tiny, their event horizons, the point of no return, are incredibly small. A mountain mass black hole the size of an atom does not have the reach to swallow a star or a planet from a distance. If one were drifting through our solar system right now, carrying the mass of the Earth compressed into something you could hold, you would not notice its pull until it was practically on top of you. So what would happen if one of these ancient ghosts actually intersected our planet? It sounds like the setup for a disaster, and yet the reality is stranger and quieter than that. If a primordial black hole with the mass of Mount Everest and the size of an atom struck the Earth, it would not blow the planet apart. Its physical cross-section is so infinitesimally small that it would pass straight through the solid rock, the boiling mantle, and the molten core as though the Earth were made of empty space. It would enter at extreme velocity, pierce the crust like an invisible needle, and exit the far side in a matter of minutes. The only evidence of its passing might be a microscopic superheated tunnel and perhaps a faint inexplicable tremor. It would behave exactly like the dark matter we observe, slipping through ordinary matter almost without touching it, leaving behind nothing but the faintest whisper of gravity. And this is the quiet vertigo hiding underneath the whole idea. It means the empty room around you may not be empty in the way you have always assumed. Every so often, on timescales far longer than a human life, one of these ancient needles may thread straight through a planet or a person and leave behind almost nothing to mark that it happened. A whisper of heat, a tremor too faint to name. The dark that holds the galaxies together may be drifting through your own street tonight, unhurried and unseen. For decades we searched for an invisible cloud of gentle particles. We may have been looking for the wrong kind of ghost all along. Part 13. The Dying Light. If a primordial black hole is perfectly invisible, and its gravitational reach is so microscopic that it could pass through the Earth without us noticing, how could humanity ever hope to prove that these things exist? You might assume they are utterly immortal, silent phantoms sealed forever behind their event horizons. But you would be wrong. The key to hunting them down comes not from their gravity, but from their death. And that revelation came from the mind of Stephen Hawking. To understand how a black hole dies, we first have to shatter the oldest myth in astrophysics. For decades, scientists believed a black hole was the ultimate cosmic dead end, a perfect one-way street where matter and light could check in, but nothing could ever check out. According to Einstein's classical theory, once you cross the event horizon, escaping would require moving faster than light, which is impossible. So a black hole should be perfectly, eternally black, growing slowly as it feeds but never giving anything back. But in the 1970s, Hawking realized that picture was incomplete. To find the true nature of a black hole, you cannot only look at gravity. You have to combine the crushing macroscopic force of general relativity with the chaotic microscopic laws of quantum mechanics. And he turned his focus to the razor-thin boundary of the event horizon itself. Remember that in quantum mechanics, empty space is never truly empty. It is a boiling sea where pairs of virtual particles, a particle and its antiparticle, constantly flicker into existence, borrowing a little energy from the universe, then instantly colliding and annihilating back into nothing. This happens everywhere, all the time, unnoticed. But what happens if one of these pairs appears at the very edge of a black hole's event horizon? The gravity there is so extreme that it can rip the pair apart before they have a chance to annihilate. One particle falls across the horizon into the singularity, while its partner is flung outward, escaping into space. To the rest of the universe, that escaping particle is no longer virtual. It has become real, carrying away a tiny scrap of genuine energy. And because energy cannot be created from nothing, the energy used to make that particle real has to be stolen directly from the mass of the black hole itself, which means the black hole is leaking, it is radiating heat, it is slowly, agonizingly bleeding its own mass away into the cold void. This is Hawking radiation. Black holes are not entirely black, and they are absolutely not immortal. They evaporate. But the mathematics of Hawking radiation hides a deeply counterintuitive rule. The rate at which a black hole evaporates is inverted relative to its size. The larger and heavier a black hole is, the colder it is, and the slower it leaks. The supermassive black holes at the centers of galaxies are so unfathomably huge that their temperature is a fraction of a degree above absolute zero. They are colder than the space around them, currently absorbing more radiation than they give off. They will take hundreds of trillions of years just to begin evaporating. Even an ordinary stellar black hole will outlive the last shining stars in the universe by an incomprehensible margin. But primordial black holes are different. As we saw, a primordial black hole can be the mass of a mountain crushed into the size of a proton, and because it is so small, its surface temperature is searingly hot. A microscopic black hole is not sitting silently in the dark. It is actively boiling away, fiercely pumping radiation out into the cosmos, losing mass at an ever-accelerating rate. This creates a terrifying runaway feedback loop. As the primordial black hole radiates, it loses mass. As it loses mass, it shrinks. As it shrinks, its temperature climbs. And as its temperature climbs, it radiates even faster. It is a death spiral that stretches across billions of years, slowly accelerating toward a final apocalyptic climax. When the black hole finally shrinks to the absolute quantum limit, it does not simply wink out. It detonates. In the final fraction of a second, the evaporation rate races toward infinity, and the black hole unleashes all its remaining mass energy, in a single catastrophic burst, erupting with the force of billions of nuclear weapons and sending a blinding flash of high-energy gamma rays screaming across the universe. And this is the exact moment humanity is trying to catch. Because when we run the numbers on Hawking radiation, we find a chilling coincidence. If a primordial black hole was born in the Big Bang, with roughly the mass of a large asteroid, a few billion tons of matter, its total evaporation lifespan would be about 13.8 billion years. That is exactly the current age of our universe, which implies that right now, hidden in the dark matter halo of the Milky Way, an entire generation of ancient asteroid mass primordial black holes are reaching the very end of their lives. They are detonating. Astronomers are pointing our most advanced space telescopes, instruments like the Fermi Gamma Ray Space Telescope, into the deep, empty voids of the galactic halo. They are not hunting for the steady glow of stars. They are hunting for isolated, incredibly violent flashes of gamma radiation that cannot be explained by any supernova or collapsing star. They are searching, in other words, for the dying screams of the Big Bang's earliest children. There is a strange poetry in the timing of it that is worth pausing on. If these objects are real, then the ones built with the mass of an asteroid have been quietly counting down their whole existence, leaking away their substance photon by photon for 13.8 billion years, and are only now, in our particular cosmic moment, arriving at the end. Which means that somewhere out in the dark halo of our own galaxy, at this very hour, one of the oldest things in the universe may be flickering out in a final burst of light. Not because of anything we did, not because of any grand cosmic event, but simply because its clock, wound at the very beginning of time, has finally run down. We happen to be alive at the exact stretch of eternity when the first generation of these ghosts is dying. It is a little like inheriting a house and discovering that its oldest candles are guttering out on the night you moved in. And if we can capture even one of those signatures, it would instantly prove that primordial black holes exist, validate Hawking's most profound theory, and revolutionize everything we thought we knew about dark matter. But even as we scan the skies for those flashes of light, another instrument, back here on Earth, has already caught something even more profound. It did not see a primordial black hole explode. It may have heard two of them collide, and the sound shook the very fabric of space-time. For most of history, human astronomy suffered from a single crippling limitation. Since our ancestors first looked up, we have depended entirely on light. Every telescope ever built, from Galileo's glass lenses to the golden mirrors of the James Webb Space Telescope, works by capturing some form of electromagnetic radiation, visible light, infrared, X-rays, radio waves. But primordial black holes emit none of it. They are perfectly dark and perfectly silent across the entire spectrum. To find a monster that is invisible to light, you cannot use a telescope at all. You have to build a machine that can feel the fabric of reality vibrating. You have to learn to listen to the universe. In 1916, Einstein predicted that space and time were not an empty static stage. He proposed that space-time is a flexible fabric that can be stretched and warped by mass, and that when two enormously massive objects like black holes orbit each other at extreme speeds, they should churn that fabric violently, sending invisible ripples of gravity racing outward at the speed of light. These are gravitational waves. For a century they remained purely theoretical, because gravity is by far the weakest of the forces. By the time a gravitational wave from a distant galaxy reaches Earth, the stretching and squeezing of space-time is so faint that it is like measuring the distance to the nearest star and detecting a change the width of a single human hair. Most physicists believed we would never build anything sensitive enough to detect it. But humanity refused to accept that limit, and we built the Laser Interferometer Gravitational Wave Observatory, known as LIGO. LIGO is not a telescope. It is a monument of extreme engineering, a pair of enormous L-shaped vacuum tubes stretching for miles across the American landscape. Inside them, scientists fire stabilized laser beams, bouncing them between the most perfectly polished mirrors ever made, suspended on glass threads to isolate them from the tremors of the Earth. The machine can detect a change in the length of those miles-long tubes 10,000 times smaller than the nucleus of a single atom. It is arguably the most sensitive measuring device our species has ever created. On the 14th of September 2015, the silence of the cosmos was finally broken. The LIGO detectors in Washington and Louisiana registered a microscopic anomaly at nearly the same instant. The laser beam shifted by a fraction of an atomic nucleus. The Earth had literally stretched and squeezed, and when supercomputers translated that distortion into an audio frequency, the scientists heard a distinct rising tone, a cosmic chirp. It was the sound of two massive black holes locked in a death spiral, colliding and merging into one. Let that land for a moment, because of everything in this story it may be the strangest. The signal LIGO caught had been travelling for more than 1 billion years. It left its home when the most complex life on Earth was still single cells drifting in the sea, and it crossed the emptiness at the speed of light the entire way, a ripple in the shape of space itself, until on one ordinary September morning it passed through the planet, through the detectors, through the bodies of the sleeping scientists, and stretched the Earth by a fraction of the width of a proton. If you slow that rising chirp down and play it aloud, it sounds almost gentle, a soft swoop upward, like a bird call or a drop of water in a still room. And that quiet sound was the last cry of two dead monsters becoming one, a collision so violent it briefly outshone every star in the visible universe, delivered to us not as light but as a tremor in the ground beneath our feet. We did not see it. We felt it. The impact was so violent that for a fraction of a second, it radiated more power than all the shining stars in all the observable galaxies combined, not as light, but as pure gravity. The community erupted in celebration. Einstein's century-old prediction had been confirmed. But as astrophysicists dissected the data from that first collision and the dozens that followed, their euphoria slowly gave way to a chilling confusion. Something about these black holes was deeply anomalous. It was hidden in their mass. By the standard models of stellar evolution, we know roughly how heavy a black hole should be when a star dies, usually somewhere between 5 and 20 times the mass of our Sun. And there is a strict forbidden zone called the mass gap, running from about 50 to 130 solar masses, where the physics of dying stars simply cannot produce a black hole at all. But LIGO was not listening to theories. It was listening to reality. In September of 2020, the LIGO collaboration announced an event that produced two black holes weighing about 85 and about 66 times the mass of our Sun, both sitting squarely inside the forbidden gap. By all the known laws of astrophysics, they should not exist. And the darker, older explanation began to rise again from the ashes. What if these colliding monsters were not the corpses of dead stars at all? What if LIGO was hearing the ancient echoes of the Big Bang, primordial black holes, unbound by the rules of stellar death, spiraling together in the deep halos of distant galaxies and ringing the bells of our detectors here on Earth? Part 14. The Last Lights in the Dark. We have officially entered a completely new era of science. We are no longer deaf to the cosmos. We have built mechanical ears that can hear the silent collisions of invisible monsters in the dark. And the discovery of those forbidden masses has violently reopened the debate on dark matter, forcing us to accept that our galaxy might be teeming with primordial singularities. But as we look toward the far future of the cosmos, we begin to realize that these ancient entities are not just relics of the past. They may be the ultimate inheritors of reality. Long after the stars burn out and the galaxies fade into darkness, the primordial black holes will be the last things left standing. Every time we look up at the night sky, we are witnessing a fragile temporary spark of light in an ocean of eternal darkness. We take the warmth of the sun and the glow of the Milky Way for granted, assuming the universe will always be a bright, busy theatre of cosmic evolution. But the truth of astrophysics is that the age of starlight is only a fleeting chapter in the grand timeline of reality. The universe is slowly running out of fuel. Right now we live in what astrophysicists call the stelliferous era, the age of stars, defined by the continuous ignition of hydrogen into brilliant galaxies. But this era is mathematically doomed to end. In roughly 100 trillion years, the last clouds of interstellar gas will be exhausted, and the universe will permanently lose the ability to forge new stars. The massive blue giants died long ago. Eventually, even the most frugal red dwarfs, the longest-lived engines in the cosmos, will fade into cold, dead embers. The galaxies will go dark, one by one, and the universe will slip into an era of eternal night. This is the beginning of the degenerate era, a time when the cosmos is populated only by the frozen corpses of planets, dead stars and wandering neutron stars. But the true rulers of that freezing wasteland will be the entities that have waited in the dark since the first microsecond of creation, the black holes. As the universe keeps expanding at an ever-accelerating rate, driven by the relentless push of dark energy, the dead galaxies will be pulled apart. The space between objects will stretch so vast that the night sky of any surviving world would be utterly black, with no neighbouring stars and no distant galaxies to be seen. And in that emptiness, the primordial black holes finally emerge from the shadows. Throughout the age of stars, they were hidden, masked by the brilliance of stellar fusion. But in the degenerate era, they are the undisputed masters of reality. Before the black hole era fully takes hold, another catastrophe may seal the fate of the physical world. Theoretical physics suggests that protons, the very building blocks of atomic nuclei, are not stable forever. Over unimaginable stretches of time, perhaps 10 to the power of 34 years, protons themselves may spontaneously decay into lighter particles and radiation. And if proton decay is real, then long before the supermassive black holes evaporate, every remaining planet, every dead star, every frozen asteroid will simply dissolve into a faint mist of glowing radiation. The solid matter that makes up everything we have ever known would be erased from existence, leaving the singularities as the only structured objects in the entire cosmos, the sole and uncontested inheritors of a decaying void. To comprehend the timescale of the black hole era, you have to abandon the human idea of time altogether. We are no longer speaking of billions or trillions of years. We are speaking of years numbered by a 1 followed by 100 zeros. Across that incomprehensible stretch of eternity, the supermassive black holes that once anchored the centres of galaxies will slowly, agonizingly boil away into the vacuum. But the primordial black holes, because of their far smaller mass, will be the first to reach their explosive climax. Imagine a universe that has been pitch black for trillions of years. No warmth, no light, no structure, the temperature a microscopic fraction above absolute zero, and then suddenly in the freezing dark a blinding flash of gamma radiation erupts. A primordial black hole has finally reached the quantum limit and detonated. For a fleeting instant, the dead universe is lit by the dying scream of something forged in the Big Bang. Millions of years later, in another corner of the void, another flash, and then another. Like solitary fireworks in a vast empty stadium, the primordial black holes will provide the final fading light show of the cosmos. When the last black hole finally evaporates, the universe enters the dark era. All complex matter has decayed. The cosmos becomes an infinite void filled with nothing but a thin, freezing mist of photons and stray particles, drifting further and further apart. Nothing will ever happen again. Time itself will lose most of its meaning, because there will be no events left to measure it. The universe will have reached its final state of maximum entropy, the ultimate thermodynamic death. It is worth letting yourself feel the strange scale of that ending, gently, the way you might look at a photograph of a place you will never visit. Everything that has ever happened, every sunrise, every ocean, every voice that ever spoke, will by then be so unimaginably far in the past that the numbers lose all meaning. And yet there is something almost peaceful in it, not frightening at all when you sit with it slowly. The universe does not end in fire or in a scream. It ends in a long, quiet cooling, a settling, like a great house going dark room by room at the end of a very long night. And the last lights to burn in that darkening house are these ancient singularities, the very first things that ever formed, seeing the story out to its close, the beginning and the ending held by the same hands. And this is the staggering legacy of the primordial black holes. They are the alpha and the omega. They were born in the infinite heat of the first microsecond, acting as the gravitational seeds that pulled the dark matter halos together and allowed the first galaxies to form. They held the young universe together, building the scaffolding on which the stars ignited and life evolved. And they will be the last surviving monuments of the cosmos, the final flickering lights before everything descends into an eternity of freezing darkness. Think about what that means for the story we started with tonight, down in the freezing tunnel beneath Geneva. We spent 40 years digging into the Earth, searching for a gentle particle to explain the missing mass of our galaxy. We assumed the universe was built on a foundation of quiet, invisible dust. But the truth may be far more violent and far more poetic. The missing mass, the phantom gravity that shapes our world, may be a swarm of ancient microscopic singularities, born in the same instant the collider is trying to recreate every time it fires. The anomalies whispering out of the quantum vacuum, the wobbling muon, the heavy W boson, The lopsided beauty quark and these silent ancient predators drifting between the stars may all be pages torn from the same unfinished book. We are surrounded by ghosts, and as we build more sensitive detectors and point our gamma-ray telescopes into the deepest voids, we are finally beginning to map their invisible empire and to listen, at last, to the quiet whispers of the Big Bang. But if the universe is truly destined to end in a freezing empty void where nothing can ever exist again, it is fair to ask what the point of any of it was. Is our universe merely a solitary doomed bubble floating in an endless abyss? The anomalies we have chased tonight, the ghosts hiding in the empty space inside the collider, all hint that our reality is far stranger than a single timeline. They hint at hidden dimensions folded just out of reach, at other universes with other laws, at a structure so much larger than the 3 dimensions we can see. And that is where this thread will carry us next, out past the confines of our dying universe and into the mind-bending architecture of the multiverse, into string theory's hidden dimensions and the possibility that everything we call reality is just one vibrating membrane in an infinite ocean of parallel worlds. For tonight, though, let the machine keep its cold vigil beneath the quiet fields of Geneva. Let the ancient singularities drift on through the dark between the stars. The ghosts in the quantum vacuum are not the end of physics. They are the beginning of a stranger and more beautiful chapter, one we've only just started to read. Rest easy. The universe has been keeping its secrets for 13.8 billion years, and it will still be there in the morning, waiting, patient as ever, for us to learn how to ask the next question.